Hi. Hopefully it's recording this time. This is my fourth time recording, so hopefully this time it works. So let's get started. Number one, we have an ideal op amp. Ideal meaning that let me just put this. Ideal means that we're gonna have I plus to equal I minus. It is going to be equal to 0, and we also know that V minus is going to be equal to V plus. We know that our I out max is plus minus 20 milliamps, and that we're going to be having plus minus 15 voltage source, and that this is our input signal. The amplitude is 1, as you can see here in the diagram, and our V out is going to be capped at 8 volts and plus minus 8 volts. So why don't we start drawing our op amp, because we need to be making an ideal op amp with an ideal load resistor. So we'll start out going like this. And we can see that V out is a linearly amplified version of Vi of t, which means that we're going to have negative feedback. So we'll design a negative feedback circuit. We'll let this be R1. It can be the op amp can be like this. This is V out. This can be the load resistor or L, like that. And then, of course, negative feedback, right? So this is Vi. And then we will have the feedback going in here. Sorry. This can be RT. And of course, like I said, there are DC currents. So this is 15, this is negative 15, but that we don't have to worry about that for our circuit analysis. So this is what we have here, and Vi equal to sine 2 pi 1000. But of course, this part doesn't really matter. We want to be designing a circuit, so we should keep going and assume that like I said before, our V plus is going to be equal to our V minus. And in this case, our V minus and our V plus is equal to VI. So because our V plus is equal to VI, that means our V minus is also equal to VI. So we're going to use that to our advantage because now we know we can do KCL. We'll see that the current going into here. So this is VI as well. We know VI over 0 minus 0, sorry. Vi minus 0 over R1 is going to be equal to this. This is VO minus VI, so VO minus VI over R2. So the current that goes to the resistor 2. So now that we have this relationship, we can keep going and say that we have VI over R1 equals to VO minus VI over R2, and that means VO minus VI times R1 equals to VI R2, meaning that VO R1 minus VI R1 equals to VI R2. We can move things around now. Say that VI R2 is equal to this. Now we can factor this out. Sorry. I think I made a mistake. Yeah, VO VI R1. Okay, and VI R2. Let's just rewrite the next line. So that means VI of R2 plus R1 is equal to VO R1. Again, we want to be getting the transfer function. So we'll keep going here and change it so we have that means VO over VI equals to R1 plus R2 over R1, which is equal to R1 over R1 plus R2 over R1 equals to 1 plus R2 over R1. This is our transfer function. Now we'll keep going. And we'll choose resistor values of R2 equals to 18K ohms. And then R1 will equal to 9K, or sorry, we'll do 2K ohms. So to reiterate the transfer function, it was VO VI equals to 1 R2 over R1. And in this case, when you plug in our values, this means that it is equal to 1 plus 18K over 9K, or sorry, 2K ohms, which is equal to 1 plus 9 equals to 10. So this is our gain. Now, in the diagram, like I mentioned before, we have it cut out at -8 and 8 for the output. So that we're going to attribute this as the I out max limit. As you can see here, it says that the I out max is plus minus 20 milliamps. So we're going to go with that knowledge. And, we already know the equation of I out max equals to plus minus 20. Okay? We know this. And we also know the equation that the I out max is going to be equal to the load current plus the feedback current. So this is the load current, and this is the feedback current. So now equating this to what we have, we know that IL equals to VO over RL plus VO minus VI over R2. Going back. So equating this to the max, we know that I out max equals to V out max over R load plus V out max minus VI max, because we're dealing in maximums now, over 18K, because that's our R2 value. So continuing our math here, we know that 20 equals to our V out max, which is going to be 8. As you can see in the diagram, it's 8 over RL plus 8 minus 1 over 18K. So moving on, we know that 20 equals RL plus 7 over 18K. That means 20 minus 7 over 18K ohms equals to 8 over RL, which means that RL is equal to 18 over 20 minus 7 over 18. When you calculate this in a calculator, it'll tell you it's equal to 0.408 kilo ohms, of course. Now, in ohms, this is going to be 408 ohms, and this is equal to RL. So just using circuit analysis and algebra, we were able to attain the value of 408 ohms for our load resistor, given the values that we have in this equation. Now let's move on to number 2. So in this question here, we have a diode, and we're gonna have to assume that it's off and assume that it's on. So first of all, assuming that the diode is off, off means it's gonna be negative VZ is gonna be less than VD, which is less than VDO. And of course, it also means that ID is equal to 0. So first of all, I think we should start by doing a KVL here. This is our input. This is our diode here. So we have minus plus VD. Current's going to go this way. And that means any current going this way will be negative of that, because this is our VO. This is going to be negative ID. Of course, we also know this is 3 volts. And yeah. So continuing, we can keep going here, assuming that VDO is 0.7 and VZ is 3 volts. So we'll do our KVL. We can see we have VI, so this here is equal to 1K ohms times negative ID minus VD plus 1K ohm times negative ID plus 3V. So first of all, in our situation, this is off. So if this is off, that means ID is equal to 0. That's equal to 0, that this is equal to 0, this is equal to 0. And then we have our KVL telling us that our circuit input voltage is going to be equal to 3 volts minus VD. Minus VD. So now that we know that this is the case, we can plug this into this relationship that we have. So we know that negative VZ is less than 3 minus VI, because that's rearranging. If you rearrange this, it tells you this. That's equal to VD, less than 0.7, because our VDO is 0.7, as they tell us over here. Now we want to isolate VI, so we're going to subtract 3 from all the sides. So it's going to be, let's see, our VZ is actually equal to negative 3. So if we subtract 3 from everything, this is going to be negative 6 less than negative VI less than 7.7 minus 3 is negative 2.3. Now we're going to change the sign for everything. So doing that, we end up getting 2.3 is less than VI, which is less than 6 volts. Now that we have this relationship here, we are going to look at the circuit again for KVL and try to analyze, get VO and VI, right? Because we have our range now, which is something they asked in the question for VI. Now we want to get VO in terms of VI. So looking at our KCL, looking at the circuit, first of all, if the diode is off, that means it's going to be open circuit. So all these other values, most of the values, well, some of these values are not going to count if it's an open circuit. So we know that VO is going to be equal to, we're going to look over here, it's going to be VI plus 1K ohm times ID. And once again, we have our ID as equal to 0 in our case. So if ID is equal to 0, this is equal to 0, meaning that meaning that VO is equal to VI. So we now know this relationship that VO equals to VI, and we know that VI has to be between 2.3 and 6 volts. 2.3 volts and 6 volts. Now going to part 2 of this problem, we're going to assume that the diode is in, it's going to be on. So if it's on, that means we have the equation VD equals VDO, and we know that VD is going to be greater than or equal to 0. Going back to the KCL that we have, or the KVL that we have, we know that VI equals to all this. I'll do it. I'll write it again. ID minus VD plus again VK plus 3. We can combine these and group them. So this is now VI equals to 2K ohms. ID. This is equal to, so we know that VD is equal to 0.7, I believe. No, sorry, we don't have that yet. So, actually we do, because because of this, we know that VD equals VDO, which is equal to 0.7. So that means we can go negative 0.7 minus 0.7 here, and then plus 3. So VI equals to 3 minus 2K ID. Okay. So now that we have this relationship, why don't we try to isolate ID? So that by doing that, we can subtract 3. So we'll do VI minus 3 divided by negative 2K ohms equals to ID. Now, if we change the signs, like, negative 1, we get ID equals to 2.3 minus VI over 2K ohms. Now, we know one of the things of the diode being on means that our ID is going to be greater than or equal to 0. So if that's the case, if the ID is greater than or equal to 0, that means also that the numerator, so this is also going to be greater than or equal to 0. So we now know what our bound is, our range is going to be 2.3 minus VI is greater than or equal to 0, meaning 2.3 is greater than or equal to VI. So our VI cannot be greater than 2.3 volts, and it cannot even be equal to that. So now that we have this, we can go back to our old KVL and get VO equals to negative VDO minus 1K times ID plus 3 volts. That means that we have, that means this is, this is negative 0.7 now. And so now we have 2.3 minus 1K times ID is equal to VO. So in order to get this in terms of VI, we want to plug in our VI ID over here, right? So we plug this in. We have 2.3 minus 1K ohms times 2.3 minus VI over 2K ohms equals VO. So that means that we have 2.3 minus, this can cross out with this. So 2.3 minus 2.3 over 2 minus negative, so it's going to be plus VI over 2. So this is going to be equal to, this is 1.15, meaning that this is all going to be 1.15. 2.3 minus 1.15 is 1.15. So now we have 1.15 minus, or sorry, plus VI over 2 is equal to V out. So thus we have a relationship between VI and V out here. And we also have the range that we have for VI. Thank you for watching, and have a good day.